Hi, welcome to the ARC Future Timber Hub Research Showcase. Today it's the Queensland Department of Agriculture and Fisheries Showcase. This is number 2 of 5 in the series. So before we begin, I'd like to introduce myself. I'm Kelly Reichmiller. I'm the ARC Future Timber Hub Manager. And today we've got Chair will be Dr. Lisa Ottenhouse. She's a lecturer at the University of Queensland School of Civil Engineering and specialises in timber structures. So a little bit about the ARC Future Timber Hub. It's an Australian Research Council industrial transformation research hub to transform future tall timber buildings. The aim of the hub is to transform the Australian timber construction industry by generating the skills, knowledge and resources that will overcome current technological and social barriers that limit the application of timber to tall structures. Our partners are experts from industry, government and academia. So we've got the Queensland Government Department of Agriculture and Fisheries, the University of Queensland, the Queensland Fire and Emergency Services, Hine Timber, Arup, Lendlease, Scion, the University of Canterbury, Griffith University and the University of British Columbia. As well as in our projects under the hub, we have individual partners depending on the project scope. We've formed a unique partnership that spans the entire timber supply chain, from primary producer to construction regulator. Our interdisciplinary team includes product manufacturers and wood scientists, architects and structural engineers, fire safety engineers and construction managers.
So the next presentation is going to be a non-destructive evaluation of elastic material properties and acoustic characterization of wood-based massive panels. And the presentation will be covering the non-destructive assessment and experimental validation process of evaluating mass timber panels for the mechanical properties. And this will include a demonstration of the rapid testing process. And the speaker is Adam Faircloth, and he is a timber engineer at DAF and also an MPhil student on project through Griffith University. He has a bachelor's in mechatronic engineering with current research focused towards vibration and acoustics and non-destructive technology. Over to you, Adam.
Thanks for the intro, and thanks, Shannon, for the really interesting presentation so far. So this project's going to be, well, is the, as Shannon said, the second project of which DAF leads 3 in the Future Timber Structures Hub, all centred around developing a non-destructive evaluation system for evaluating CLT mechanical properties. There we go. So this talk's going to be broken down into about 5 steps. I'm going to go through the bit of a background and introduction, and then lead into the aim of why we went with the direction we did for this project, and why it's necessary, the developed vibration methodology that we found through literature and what we've adopted, how we validated our results, and what results we've gotten so far, as well as outcomes and benefits that this project would have to the timber industry. But quickly, before I go too far, I'd like to acknowledge collaborators directly with this project. So we've got XLAM, Hine Timbers, Lendlease and Arup, as well as Griffith University being the institution of where I'm doing my masters. And on the right hand side there's a list of my supervisory team. My principal supervisors, Dr. Hassan Karanpour, Dr. Stephen So at the university, and then Dr. Chandan Kumar, Dr. Loic Brancheroux and Dr. Henry Belliers are my external supervisors. Loic is based in France at the Centre for International Research and Agricultural Development. Henry is based at Hine Timbers as a product development manager, and Chandan works with me here at Salisbury. So a bit of introduction about wood-based mass panels. Widely used and becoming a more commonly accepted building material for mid to low rise structures. And they provide a lightweight and cost-effective alternative to common construction techniques such as steel and concrete. For example, in this image here is a photo from construction at the Monterey building, an apartment building at Kangaroo Point, which came about as a position above the Clem 7 tunnel in Brisbane. They couldn't obviously make it too heavy due to it being above the tunnel. So using timber as a lightweight alternative was a great use for the product. So with wood-based mass panels, there's a wide range of different variations to them, such as glulam, which are glue laminated timber panels, timber beams, cross-laminated timber, CLT, nail laminated timber, which are fixed with nail fasteners rather than adhesive, and veneer-based mass panels. For this study, we decided to focus on a more mainstream, or the most mainstream product, which is CLT. CLT is most commonly used for, or is commonly used as both a flooring and a wall product, but most applicable to a flooring or a ceiling element due to their large spanning applications. Panels can be designed to whatever requirement. Basically, the only restriction is whatever the size of the truck is that's taking them on site. So cross-laminated timber is cross-directional layering of different boards where each layer reinforces the previous one along the major axis, which is along the face grain of the baseboards, produces obviously a stiffer result than the minor axis, which is perpendicular to the baseboards. And the design of CLT or glulam composite systems more so governed by their serviceability rather than their ultimate strength, which means by determining the mechanical properties such as elastic modulus and shear modulus, we can determine the application for these products rather than going off of how strong they are. So for determining these mechanical properties, there's two common methods that industry uses, one of which being an averaging or pre-manufacturing technique. This makes use of non-destructive evaluation technology for boards, which is well established in the industry. The boards are non-destructively evaluated, and then almost as they're put into a panel, each value averaged together to give a single result for how the panel would perform. The second method, which is a post-manufacturing technique, is a static testing method, which, as you can see in the top left figure, consists of a 4-point bending configuration where load is applied at a constant rate and deflection is measured about the midpoint over the duration of the test. From this test method, we get a load versus displacement curve, so you can see in the bottom left, from which we can determine stiffness. These tests, the static testing method is accurate and efficient, although can be costly and time consuming to conduct, as well as destructive at times. As I said before, non-destructive techniques are available for beams and boards, although no such system has been developed for cross-laminated timber panels to be used in situ within a manufacturing facility. And to the research team's knowledge, we couldn't find any system that's currently being used for CLT in Australia. Which brings us to the aim of this project, which was to research, develop, and validate a non-destructive evaluation system for CLT panels for use within an inline application for a manufacturing facility. This could be summarised into about 4 points of what we aim to do. One was to develop a vibrational-based evaluation program, software and methodology to calculate the mechanical properties of CLT. The second, to investigate the in situ testing requirements, such as how the panel is going to be supported during the tests, and how can we ensure that a rapid technique is being used. The third being to validate these experimental results, of course, from the first 2 points through standard testing methods. And then the fourth, to investigate the accuracy of the theoretical and experimental comparison that we're doing through the experimental tests that we conduct in the first 2 points and theoretical modelling that we've conducted. So first, the methodology that we've adopted has been previously investigated back in 2008 by Renee Steiger, which is based on a two-pronged approach, where in the, I guess, the above half of the slide shows the experimental modal analysis. Yeah, the panel is supported by whatever boundary condition is selected and tested along an array of points to obtain both impact data and acceleration based on a using a surface-mounted vibration sensor accelerometer. From that, and taking the frequency transform of those results, we obtain resonant frequencies for those responses at each point along the panel. At the same time, theoretical model analysis or simulations are conducted of the panel using the known geometrical properties, size, dimensions, weight, as well as some elastic estimations for stiffness and shear. Then combining the results of those two approaches, we can then refine the elastic estimations that the model makes until the error between the two methods becomes very small or nothing. But before we could get into too much testing, we needed to know what boundary condition would be, one, best for industry, and two, give us the most repeatable and efficient or accurate results. So looking at a detailed literature review that we've conducted, we found there were varying results from published literature on what boundary conditions suited best for what applications. So we picked the following 6 boundary conditions for use. The first one being a simply supported and freely supported boundary condition, where each parallel edge is either freely or simply supported by sitting on the horses that you can see at the bottom of the picture, or sitting on air, not supported at all. The third condition, which was a freely supported system hanging using elastic recovery straps. The fourth being a simply supported on all sides configuration, where the panel was sitting on a wooden frame that we've constructed. The fifth being, again, another freely supported condition, but this time on edge, using those same recovery straps. And the sixth method being again, another freely supported condition, but this time using an air bladder or airbag setup. So these tests are conducted quite quickly and easily using minimal equipment as well. So all we needed for these tests was an accelerometer to measure the vibrations and an impactor, or for these tests we use an electronic impact hammer. As you can see in the top left figure, an impact is applied to the panel at one corner and the impulse measured at the next. From that, taking the FFT of that result, we get a frequency spectrum that looks something like that. From testing each of those boundary conditions, we found that, one, the freely supported conditions provided the clearest and highest quality results. In the box plot on the bottom right, you can see a plot of the quality factor, which represents the clearness or the cleanness of the signal that we obtained in the frequency spectrum. And it shows that the 3 freely supported conditions by far surpass the other 3 simply supported or simply supported free configurations. From that, we found that the air bladders or airbags presented the most repeatable, but also the easiest for industry to then apply to an inline application. We also found with those air bladders that the pressure being used within them to inflate them did have some effect on the system's ability to obtain certain frequencies. As you can see in the top right hand plot, this is an overlay of varying pressures, and you can see that there is some shift in frequencies for some modes, some dampening of other modes, and some joining with modes as well. The next investigation that we decided to conduct after we were happy with our boundary condition being the airbags, was to look at the geometrical sensitivity. So if we were to scale up from the common panels that we were using for those boundary condition tests to a longer length, how would our system be able to cope with that kind of change? So using the UQ facility at Pinjarra Hills, we were able to get access to some larger panels and some larger sample sizes. Using a panel at 6 meters long by 2.4 meters, we conducted 4 impact tests using the accelerometer moving at the different positions, as you can see there on the figure. Those panels were then cut in half and tested on the 2 sub-panels to give a comparative result. Results show, those graphs do look a little bit sporadic, but positions 1 and 3 show that there were some frequencies missing and amplitudes dampened, where in position 2 and 4, there was a lot more frequencies available. What this means is that position 1 and 3 being at the center of each of the minor and major directions, dampened some bending modes. So by having the position or the accelerometer at position 2 and 4, we were able to obtain all frequencies that were required for evaluating the panel's mechanical properties. Moving into the theoretical component of the method, we looked at, I guess, the influence of shear as a known obstacle for theoretical analysis of panels or large beams. For panels with a length to thickness ratio of anything greater than 20, a thin plate theory or thin beam theory applies, which means that the shearing in the panel doesn't need to be considered, and it isn't considered as being influential to the stiffness determination. Although for panels with a ratio of less than or equal to 20, the length to thickness, that shear becomes more influential on the result and needs to be considered. Best way of explaining it is in the bottom left figure there, shows a cross-sectional bending moment with two theories that govern it. The first being the Ulla-Bernoulli thin plate theory, which shows the neglection of the shear. If that was to be applied to a thick panel with a ratio of less than or equal to 10, this would over-predict frequencies, under-predict frequencies and over-predict the displacement, which means that you would get a higher stiffness result for something that wasn't as obviously that stiff. So then moving on from that to the modal reconstruction component that we wanted to look into, so that we wanted to make sure that the frequencies that we were obtaining and for what mode that we were saying they were for matched with our simulation result. So to investigate this, we did as similar to the method that Renee Steiger used for their assessments, assessment of the whole panel across different array of points for the boundary conditions that we selected, which then gave us an acceleration value using the accelerometer, of course. By then integrating that twice to get displacement, we were able to generate mode shapes. So here, if we know the displacement and we know the position at which it's being tested, we can reconstruct those modes. Results from this study are still being investigated, but preliminary analysis found that we were able to match accurately the mode shapes from the first 4 to 5 modes for a freely supported boundary condition, and comparing experimental frequency results with the simulated frequency results, we were able to get up to about the 12th mode within a 10% agreement. This shows that while we're obtaining correct frequencies, the mode shapes that we're generating or displacements that we're observing with the sensor may not be correct, but we're still investigating some of these causes. Comparing other boundary conditions that we investigated gave varying results with larger errors than the freely supported systems. So for the validation component of the study, once we've conducted the experimental results and the theoretical analysis, we needed to validate to make sure that the results we were getting from our model non-destructively match up with the predicted values that would be obtained from static testing. So taking those 6-metre billets that we obtained from the Pinjarra Hills site, cutting them in half to 2 3-metre subpanels, we then cut 2 strip specimens from the edges of the panel. These sections were cut to 0.3 metres or 300 millimetres in width to meet the requirements for the international standard for CLT testing 16351. These specimens were then tested on a 4-point configuration as introduced earlier. Summary of results: all the NDE testing had been conducted and large-scale trials completed. We assessed a range of different panels and different thicknesses, ranging from 75 mils to 150 mils, with varying laminate layers from 3 layers to 5 layers. In total, about 80 static tests were conducted, and so far we've got a pretty good agreement between 10 to 15% error between our non-destructive result in comparison with our static testing result. Results for the thicker panels are still being analysed, as well as any differences between the thick and thin plate theory. So further work to be conducted. We still have a bit of work to do in terms of analysis of the elastic and the shear modulus results to make sure that we're getting correct values in combination with our static tests, as well as finalising and fine-tuning our software and the interface. A bit of a summary of what we've done so far in terms of outputs from the project. To date, we've presented at 3 conferences so far, with 1 paper currently in review and 3 more underway and planned. And final reporting and an operations manual of our software is close to being completed. And that's me. Thank you very much. If you have any questions, feel free to email myself or Shannon, or leave your questions to the end.
And just to finish off, tomorrow we've got the Griffith University Showcase. There will be 2 presentations, one on the progressive collapse, robustness, resistance of post and beam mass timber buildings, and the second on the optimisation of wood-based mass panels for Australian building systems. The second presentation is the 3rd DAF project within the hub. Thank you everyone for attending.
Thank you for attending, and hopefully we'll see you tomorrow. If you've got any questions, feel free to email. Thank you.